So hello everyone, and so this is me live welcoming everyone to this session. We are very happy to be hosting Dr. Harshad Khadilkar as our speaker for today. So Harshad is a senior scientist at TCS Research, but is also an adjunct faculty at IIT Bombay, and he also holds an affiliate position with the AI Center at IIT Bombay, CMIND. And we're also very happy that he is an associate researcher with RBCDSAI as well. So Harshad has done some fantastic work in applying reinforcement learning ideas and control theory ideas to very hard real world problems, and both in terms of getting the application to work, but also getting more useful theoretical insights into while solving these hard problems. Right. So I'm very happy that Harshad agreed to talk to us today. And so Harshad also has a undergrad degree from IIT Bombay and a master's and a PhD from MIT. And before he came back and he first joined IBM and then moved to TCS Research. So we are very happy that Harshad is with us today, and also in general happy that he's in the Indian research ecosystem. So thank you, Harshad, and over to you.
Thank you, Professor Ravindran. I'll share my screen. Please let me know that you can see it.
Okay.
Is it visible?
Yes.
Okay, excellent. So thank you for this invitation, Professor Ravindran, and thank you to everybody for showing up despite it being a pretty bad week weather-wise. So I'll be splitting this talk into 3 different sections. Now, typically I prefer to keep it informal and let people ask questions. But right now, I think in this system that has been set up, I think people will not be able to unmute to ask questions. But please feel free to put your questions in the Q&A box and we'll pick them up at the end as far as possible. So I've split this talk into 3 parts. So one, I'll try to give the context for why we are at TCS are looking at using reinforcement learning in particular and AI in general for various industrial control applications and why it makes sense for us to look at it right now. Let me see if I can move this away. Yeah. In the second part, I'll actually talk about some of the applications that we have looked at. And in the third part, I will talk about some research questions that have popped up because of the application work that we have been doing in reinforcement learning. So to start with, I want to give the context for what we do at TCS Research in my team. We are about 12 people, mostly with masters and PhDs, and a couple of people with bachelors. Our goal is to deploy reinforcement learning algorithms in industrial systems to improve their efficiency efficiently, right? So the efficiency part is obviously the optimality of how various operations happen in the industrial system. And the second adverb, the efficiently part of it, is talking about using a relatively small amount of resources in terms of computation for inference as well as for training when we are developing these algorithms. So that's really the dual goal, and it is somewhat different from the reinforcement learning approaches that are in the majority in published literature, where you don't typically care about the computational aspects and you assume that a fair amount of compute is available. So how can we actually think about making the industrial systems more efficient with the minimum computational resources? Well, the first thing we want to do is we want to leverage whatever domain expertise exists in the system. Okay, so if we are looking at something like a railway system, we know that railway controllers have been working on this problem for over 100 years, right? So there is a lot of native intelligence in the whole business domain people that are operating the system, which we want to leverage as much as possible. Not only do we want to use their help in setting up the problem, in defining the reinforcement learning problem, but we also want to work as far as possible with any existing algorithms that are in there that make sense, either because they complement what reinforcement learning is good as, or because they exist anyway as the underlying algorithms for other agents in the environment. So in both those cases, we want to work with existing algorithms, mostly heuristics as far as possible. And in this diagram at the bottom, I have kind of shown what the system of today looks like in most industries. So you have the system box here, which is covering everything that you're trying to control. So it could be a manufacturing floor, it could be a transportation system, it could be a railway network, whatever it is. It is throwing out a lot of data already. There are a lot of sensors usually embedded in these systems today. They generate big data using IoT sensors and so on. And these sensors generate a set of features that even today a lot of machine learning or AI algorithms use to generate forecasts, alerts, to identify anomalies, and so on. Okay, but then these forecasts and alerts are typically given to a human operator who uses his or her intuition and experience to decide what to do about it. Okay, and this for us is where the bottleneck lies in most cases in normal operations. Right? Obviously, a human is critical when something anomalous happens and you have to do something out of the box. Obviously, artificial intelligence algorithms or any data driven algorithms are not going to do something very imaginative or creative that they have been not been trained to do, and for that you need humans. But our proposal is that for day to day operations, when everything is happening as normal or close to normal, uh, using a person to do every single action every single time is a bottleneck. And so we would like to move this person up into a supervisory role and plug in a reinforcement learning algorithm over here, which can close the loop efficiently, and you can have a human overseeing operations. So that's really what we are trying to do in a nutshell. Now, I also want to talk about why we need AIML in industry right now. And to do that, we first have to look at what the state of the art is in industrial operations right now. And I can probably classify all algorithms that underlie industrial operations into two parts. One is heuristics, which are essentially rule based systems that have been defined by humans. So you use a lot of offline human knowledge and aggregated intelligence to define these heuristics. And then once you're given a new problem for, say, the upcoming week or the upcoming month or even the next few minutes, these heuristics operate in the sense of taking fixed decisions. Given the input, you take a set of fixed decisions, if then else kind of rules, and you generate a solution. So it's quite fast, but it also very static, right? So every time you give the same problem, there's no scope for improvement. As time progresses, what has been coded into the system is what is going to happen every time. The second set of algorithms do react and try to improve over time. And the idea is that these programs use meta heuristics such as genetic algorithms or simulated annealing and so on. And so they have this online curiosity and exploration where, given a problem, they will try to find the best solutions in a specified time limit, and they will give out the best solution that they can find. The problem with this is that they typically start from scratch every time, and so it takes a long time to find good solutions with this kind of local neighborhood search. And so, what we want to do is to combine both these aspects, the aggregated intelligence as well as the curiosity and exploration, do it all offline, so that the whole corpus of human knowledge, as well as whatever curiosity, exploration, trials that the algorithm wants to do, is all done offline in the pre-training portion of the deployment. And then once you have this, the aggregated intelligence is then plugged into this AI system, which, given the problem, is going to produce a one shot solution. But it is not static, because whenever the solution is produced, there is a feedback loop that goes into the aggregated intelligence box in the form of memory or experience replay. And so whenever you want to retrain the system, you can get an improved policy, hopefully. So that is what we want to do. Now, most of what we have done so far, I would not classify as pure reinforcement learning. So it's not a purist view of RL where you give it the state space and the actions and the reward and then let it figure out everything on its own. What we have found is that it takes a very long time and a lot of computational resources to get a system to learn in that kind of scenario, and the eventual solution that you get may be a few percentage points better than what you would with, say, a heuristics plus RL kind of approach, but typically it's not a worthwhile trade-off economically speaking. So that's why we tend to use not very pure forms of reinforcement learning, but RL with some amount of help from other algorithms. Now, the key question for us really when we look at real world problems is this. Okay, so the typical reinforcement learning problem starts from this very familiar Bellman's equation where you have the Q value of a state action pair being the current reward plus discount times max over the next Q values. And you have a transition function for for generating S prime given the current state and the action. And then there's a huge corpus of literature on how to solve this problem efficiently depending on various forms of q, whether you want to use policy gradients or value based algorithms or a mix of them, on or off policy and so on, right? So there's a lot of literature that exists for solving many different forms of this problem. Our issue with real world problems is that defining these equations in analytical form is itself a very big challenge. Even if we think about doing it in simulation, it is still challenging. So we'll come to specific examples a little later, but our difficulty, I would say, in solving real world problems using RL or in fact any analytical or formal optimization method is to define what is the right state space for this problem. What is the action space we want to give to the algorithm? How do we shape the reward? Typically, I mean, there's no obvious reward such as you have in a game where if you win, you get a +1. If you lose, you get a -1. If it's a draw, you get a 0. It's a fairly obvious reward function to use in games, but in real world systems, there isn't something as obvious as that. You don't really win or lose, right? Unless you are in a very specific environment, such as, say, auctions and so on. And then the transition functions themselves are unknown. Many a times you don't have enough information about the system to model them exactly. Sometimes you don't have the time to capture everything in detail to get this right. You want to do something more approximate, and something even as simple as defining the discount factor for future rewards is not very obvious. Right? And we'll start looking at some real world examples of this. And I mean, as a primer, there is this problem which is very familiar to everybody, and that's why I put it first. So what we want to do here is to solve the capacitated vehicle routing problem with a small added complication of timing windows for each customer. Right. So the setup is as follows. You have a central depot over here where you have a number of vehicles that are sitting there at the start of the day. Each vehicle has a maximum range or maybe a maximum capacity of how much goods they can carry at any given time. Oops, sorry. And your goal, and there are a bunch of customers which may or may not be available at the start of the day. So some of them are known initially, some of them may pop up during the day, and each customer comes with a specific amount of demand. So I want this much material between Tmin and Tmax. Right? So every customer is going to specify his or her own minimum and maximum time window during which the vehicle has to reach there. And there's a finite amount of time required to service the customer, and obviously a finite amount of time required to travel between any pair of customers. And so what we want to do is to find the best set of routes and the minimum number of vehicles that is required to service your entire demand over the course of the day. Now, to think about it in concept, this is quite a simple problem, but defining even the trade-off between how much additional distance are you willing to send a single vehicle on in order to not have to invoke a new vehicle, right? So to give you an example, suppose vehicle range was not an issue and you could serve all five of these customers using a single vehicle. So you could do it, but then it might take a very long time over the course of the day to do it, and the person who is driving it might get tired. So it's not clear that the best solution is always to just send a single vehicle to serve everybody. Maybe you're already paying for the second vehicle and the second driver, so you might as well use them. Or sometimes it might be that serving these two guys quickly and then the other three quickly is not even a quantitative a good thing, but it's a qualitative thing because the customer perceives a better service quality, right? So if you book something, say on Big Basket, and you wanted it anytime before the evening, but if it arrives in an hour, you are still impressed, right? So that is something which is not easy to capture in quantitative terms. Okay, so solving even something as simple as this is quite easy technically once we have defined the problem in numbers, but actually defining the problem itself can become a challenge, and that is where the art part of reinforcement learning comes in really. So to make it more concrete, what I perceive as the gap between doing RL theoretically and actually trying to apply RL in real world, I can put it into four boxes. There may be more, but I would say there are at least these four. The first and most important of these I've kind of mentioned tangentially already, which is that there may not be a compact representation of a problem, right? So there's a contrast here where you have this Super Mario game, which by itself is quite a complex RL environment, but it still has a very fixed and well-defined set of rules as to what can happen and what cannot happen. Right? It's not possible for Mario to get a call in between from Luigi asking him to come back with some vegetables when he's done. Right? So this kind of thing cannot happen in the game, but it can happen in real life. So the example I've shown here is that of loading a ship using containers from the yard, and we want to decide the optimal set of containers and the sequence in which they should be loaded onto the ship so that it is loaded in the minimum possible time, right? So you could do a very good plan based on what you perceive as the state of the yard, but maybe there are other ships being loaded at the same time, and some containers have moved by the time you have done, say, the first five containers. So should you recompute a new solution or should you not? Or even if you're building a simulation for solving this problem, should you consider parallel ship loading or not? Right? These are design decisions for which there is no quantitative answer. It's a qualitative decision that you have to take as to what complexity you are willing to put into the simulation. The second problem is that of variable and very large dimension size. So in the case of most theoretical problems, the popular ones like chess or tic-tac-toe, you have a fixed input size, right? So there's a fixed board and there's a fixed number of pieces on that board, and they all have well-defined behavior. But in real world problems such as, say, a railway scheduling problem, every railway line is going to be different. On different days, the same railway line will be carrying a different number of trains and so on. Right? Sometimes your tracks may be shut down for maintenance, sometimes they may be open. Sometimes there might be a train broken down on one piece of track which is not usable for part of the day and so on. So there's all sorts of complexities which keeps changing the size of the problem from day to day or from run to run. And that's something we have to build into the RL solution itself. Otherwise, we will not be able to use it for a long term. It would be very, very specific to a single problem instance. The third problem is that of computational effort. So this screenshot, I'm sure you can figure out, is from OpenAI 5's original blog on how much compute they were putting into their OpenAI bot. I forgot the name of the bot, but it's a huge amount of compute that they are pushing into the training. And most of our customers, speaking as a TCS scientist, would not have anywhere near this, or even if they had the financial cloud, they would not commit so many resources to solving, say, one of their problems, right? So we have to do it with reasonable computational effort. And the fourth and most important thing is, after you have solved everything, you have defined the problem, you have solved it, you have got very good policies. If you cannot explain to the business user what the policy is doing, right? And I'm not even speaking in a very technical explainable AI context. I'm just speaking from the perception of what the policy is doing versus what has happened in the system so far when people were working on it. If there is a huge amount of difference and a sudden difference between what the policy does and what people used to do, they will not accept it, right? So either you have to justify it quantitatively, you have to show what the trend policy looks like. So in this case, I'm showing an example from one of our papers on supply chain inventory management, in which we are plotting with a heat map how much inventory replenishment is requested based on the upcoming forecast and the current inventory levels. Right. So unless you can justify your decisions to some extent using these kind of approaches, it will never find acceptance in real world systems, even though you may have actually solved the problem very well. Right. So overall, the takeaway from this slide is that we have to include existing domain knowledge to reduce computational effort, to model the problem compactly, etc. And we have to introduce these changes gradually and with more transparency than what typical deep learning methods offer, in order to actually make it work in real life, or to at least encourage people to use it in real life. So this is the first example that I want to look at, just because it is very easy to relate to for everybody. Right. So this was something we did in March and April of last year, just after the pandemic hit, and we were kind of at a loose end as to what to do because people had moved to remote working and so on. And we were also experiencing these very different lockdown policies that were happening all over the world and even within India, right? So the people were throwing out decisions, governments were doing it at a city level, state level, national level, and there was very little quantitative justification as to why certain decisions were taken or not taken, right? So we said, let's look at, or at least let's try to use reinforcement learning and see if it can produce a more quantitatively justifiable set of lockdown decisions, right? So that was why we started doing this. This was not actually a purely TCS effort. It was with colleagues in Microsoft Research. uh, so the idea was that we built two very simple components into our environment. One was the disease model as we understood it in the middle of last year, at the start of the pandemic, where the idea was you have a susceptible state for every person who may or may not get the disease. You have a susceptible state, then they could become exposed to the virus. About 80% of them became infected and symptomatic. 20% became infected but were asymptomatic. We assumed that all the asymptomatic people recovered, whereas among the symptomatic people, maybe 98% recovered and 2% did not. And at that time, there was no data about reinfections and so on. So there was no backward arrow from recovered to susceptible. Right? So it was a very simple disease model with time lags, obviously, for incubation and so on. And we also had a very simple network model for India, where we said, let's assume that the connectivity or the number of people traveling between any two districts in the country, we have about 700 districts in India. The travel between any two districts is proportional to the product of their populations and inversely proportional to the either the distance or the square root of distance, one of those two. So it was a very simple network flow model. And using just these two components, we said, let's first try to see whether we can model the real world data sufficiently well. And I'll show you some validation results in the next two slides. But once that was validated, our goal was, let's see if we can use the information about infections detected, the connectivity that we were talking about, the strictness of enforcement, and so on, and come up with a district level RL agent which can be reused for all different districts, right? So you have a single trained policy. Which is going to be repeatedly used, but you will have different inputs for different districts. And the output would be a very simple binary decision that says, should you lock down this district for the next week or should you keep it open for the next week? And the rewards would be based on balance between economic cost and healthcare cost, right? Which parameters you could control as a user. So really the idea was that you could play around with the system from the perspective of government and try and at least see what the likely effects of any decisions were going to be. Right. So on the left, or rather, let's leave the left hand side out for now. This is the validation result, but let's look at the plots on the right. So the reward is not really anything meaningful in terms of what it means in terms of value, but we could see that the training was fairly stable over many different random seeds. And the policy was very simple. So we had a bunch of inputs. I think there were 8 or 9 inputs that we were using to decide whether to lock down a district or not. But we found that sometimes some of these inputs were more important than others, right? So in this example, we saw that the number of people who were symptomatic in the current district and the number of people who were symptomatic in the country as a whole, those were the two most important inputs. And there was a trade-off. So all of the black dots that you're seeing is a recommendation that the district remain open, and the red ones are a recommendation that the district remain closed. And obviously, I mean, this policy is parameterized by the weights that we had placed on healthcare versus economic cost. Right, so it was a very simple output. Anybody could understand it once the policy was trained. And finally, we can come to the left-hand side now, where we are looking at the validation results. Okay, so uh, the blue curve here is multiple random runs of the model with decisions as were actually implemented in India, right? So there is a single day of lockdown on March 22nd, and then March 25th onwards, you have continuous lockdown. And I mean, we had some real world assumptions about how strictly the lockdown would be enforced and how many of the symptomatic people would actually be captured and how many of the asymptomatics would be captured and so on. Right. So we were not using the state variables, we were using realistic observations. And the blue curve is our prediction, the model's prediction of what the number of active cases would look like over time. And the red and black curves are actual real world data that we were getting, public data sets. So this was quite a short period, less than a month, but we kind of used this model and predicted what would happen uh, up to the end of June, which is on the top left here. So in this case, the model is still being trained only on data up to April 19th. And after that, it's just been projected. So the blue curve shows that the total cases would rise over 1 million by the end of June. And by, I mean, from the real world data, we could see that we were quite close. We were at about 800,000 cases by the end of June. Most strikingly, on the bottom right is our projection of what would happen even if the lockdowns were kept in place for a whole year, given what we could observe about how strictly lockdowns were enforced and how easily people were breaking quarantine and so on. And we saw that you could get more than 10 million active cases around the October-November timeframe. So at that time, we thought that this was quite unrealistic and that we would have to recalibrate all the time. But unfortunately, this turned out to be not so unrealistic. But I mean, that's a discussion for another day. Uh, but with that segue into some of the things that I talked about how closely we want to model something in simulation and how do we get it to work on with reasonable computational resources on variable data sets and so on. uh, this whole aspect did not come out of the blue. We were already using similar ideas in our real world use cases in TCS. So this was an example from the railway network. So we have been working with Konkan Railway Network for about 7 years now. Uh, the idea was that originally in the year 2000, the Konkan Railway line was set up as a single line going north to south on India's west coast, and it was designed to carry about 50 trains per day. But now it is carrying more than 90 trains per day, and obviously this has caused a lot of delays. And while you can use real, formal optimization methods to solve for a timetable, which you can use for the whole season, if you enter a delayed state, every delayed state is different. So you can't really use something that takes a long computational time to recover from the delay. And so we thought we could use this reinforcement learning concept to try and recover from delays more efficiently, with the goal of reducing secondary effects, right? A secondary effect is that when one train is delayed, because it is blocking resources that it was not expected to block, it can delay other trains as well. And those trains delay other trains and so on, right? So this spreads. So we wanted to minimize that secondary delay effect by using RL. And the solution we came up with was very simple. So you just look at the local horizon around a given train. So in every time step, you first select a train which is due for a move into the next resource. This next resource could be entering a station or leaving a station after its halt. And for this train, you look a few resources ahead and a few resources behind. You map it to a fixed state space, with these different colors indicating whether the resources are free in green, almost full in yellow, and completely full in red. And you decide whether you want to move into the next resource or not. Right. So it's a very simple RL model. Again, binary, which is the inspiration for the COVID lockdown model as well. So it's a binary decision whether to move into the next resource or not. And if you don't move, you just wait for a minute and you try to compute the decision again. Right? By that time, other trains will have moved. So you will see a change in the state space, even though you don't take any action right now. So this was quite successful in a POC, but I mean, right now it's not been deployed on the real world system in the actual active use. The second example is about robotic parcel loading. And in fact, one of Professor Ravindran's former students was working with us for his internship when we were doing this project. So he contributed to this as well. The problem here was that you have, say, a courier or logistics company on which is receiving a lot of parcels, say, collecting everything in Bombay. They're putting them into larger bins, putting those bins onto a truck, which then goes long distance, maybe to Chennai, and then you again unpack everything, right? So to pack these bins, we can use robotic arms. They already exist and they know how to manipulate parcels, boxes, and so on, but you don't know where each parcel should go to maximize the volume utilization. So for that, we were trying to use reinforcement learning. And the first instinct you have as an RL researcher when you see this problem is that you look at the current state of the bin as an image input, say a top-down view. You look at the dimensions of the parcel as a second channel input, and you just have a policy algorithm that tells you where the parcel should go. Right. So that's obviously what we tried initially as well, but we soon found that it's very, very hard to get a deep neural network to learn geometry. Right. So to predict what will happen to the bin if I place this parcel in a specific location in the bin in a specific orientation, it is very, very hard to do. But then we had an epiphany and we discovered that we know how to do this, right? So if I tell you specifically where the parcel is going to be placed and in what orientation, you can just have a simple addition function that tells you what the bin will look like after loading, right? So with that simplification, what we did was we'll forget about the policy algorithms. We'll just give it possible snapshots of the future bin, right, by loading the parcel hypothetically in various different places and let the RL algorithm figure out which one it likes best. right? And now we can use all sorts of domain expertise because we can shortlist which positions are more promising, which orientations are more promising. We can have look aheads for upcoming parcels and all sorts of things, right? So we can give it a fixed list of possible future states, and the RL algorithm can pick which one it likes best. Right. So with that, the difference, we were able to show quite good results in packing bins as well. Returning to the vehicle routing problem, again, we had to simplify this work. So there are a lot of papers already in literature on solving constrained VRP, right? So you have pointer networks, you have a lot of possibilities, including decision transformers, which do a simple version of VRP and so on. But what we really needed was something that could work at very large scale. So if you have 100 vehicles and thousands of nodes, and in a very dynamic environment, right? So you have demands coming up all the time. Maybe somebody goes away after waiting, and so the demand can also disappear, and so on. And we found that if we just take very simple decisions for by computing the value of each vehicle and each customer pair, right? So we just look at which pairs of customers and vehicles give us the best predicted values and start moving there. It actually gives us fairly good solutions, say within 15% of the known optimal ones on benchmark problems, both in terms of number of vehicles required and the distance traveled by those vehicles. And we can do it in a thousandth of the time that exact optimization takes. Right. So I wouldn't say that this problem is solved as an RL problem, at least by us right now. But we have got a solution that's good enough to implement in business and see, some real world impact. Right. So, but I would still classify this as work in progress. And then we have a couple of examples of what we've done in the retail industry, right? So this problem, in fact, you will see once I've explained it, is not very difficult to solve using RL at all, but the modeling itself is the tricky part, right? So on the left-hand side is the actual situation. Okay, so on the top, you have what currently happens when you order something on, say, Amazon. Okay, so oops, so you will have noticed that there is a note underneath every item when you go to book it that says order within the next so and so minutes to get next day delivery. Right, so that deadline is computed essentially by tracking backwards as to how long that item is going to take to come to your doorstep, and that includes time in the warehouse, in which in the case of very large retailers can be huge stadium sized warehouses, right? So it could take a couple of hours just to find it in the warehouse, put it on a conveyor belt, get it to the exit station, package it, slap a label on it, and put on the truck, right? So that itself can take 2 hours. Then maybe loading of the truck takes half an hour, and the truck itself takes 3 hours to come to your doorstep. So overall, it says it needs 5.5 hours to get that parcel to you, and so the website displays your deadline when you try to, look for next day delivery. So that's what happens currently, and all of this is very very strongly optimized, right? So there's no way to actually reduce the amount of time it takes to do these individual steps. And so what we tried to look at was, can we actually preempt some of these steps and start moving the parcel out before you even place the order, right? So on a given day, I know that if say a World Cup match is coming up, people are going to order India t-shirts, right? So I start moving out my India t-shirts from the warehouse in advance, using only whatever residual capacity is available, right? So there's a trade-off as to how confident you are about your prediction that so many shirts will be ordered versus what is the revenue margin that this item gives you, right? So maybe there's a very high margin item like a LED TV, which has low probability but the potential for high reward. So you have to trade off your capacity as to whether to pick up the TV or to pick up these uniforms. And that is why it is an RL problem and not just a pure supervised learning problem. So you start moving out these items that your RL algorithm has chucked out as orders. And when you actually place an order for the item, this item is hopefully very close to the packing area already. So you just slap a label on it and you put it on the truck. Right. So you can deliver the same item to your doorstep in 3.5 hours instead of 5.5 hours without changing any of the processes involved. Right. So that's what we tried to do. And this is what we published in Chords Command last year. And so the actual problem then is quite simple, because it turns out that there is a nice way to actually compute the reward uh, based on what your capacity is available and how much margin you are able to add on to your existing operations. And so solving the RL problem becomes relatively simple. And finally, it's not just single agent systems that we have been looking at. In fact, the Professor Ravindran is advising on this work that's on the slide now, where we are trying to set up an inventory replenishment system for very large retailers using multi-agent reinforcement learning. It is not very complex right now, but you still have all the multi-agent aspects of reward sharing, information sharing, and so on. And the idea is that we will convert. So the goal of the system is to get products flowing from the suppliers, whether they are farms or factories, through very large regional warehouses to smaller warehouses and into the stores or directly to your doorstep. Right. So it could be e-commerce or it could be brick and mortar stores. And the tough problem really is that it is hard to use whatever capacity you have to keep all the various products in your range stocked to the correct level. Right. So doing it for a single product is quite easy. You know how much to replenish. But when you're trading off the capacity for, say, 100,000 products, it becomes very hard. And so we have come up with a design where each store is an RL agent in itself, each warehouse is an RL agent in itself, and so on. Essentially, all of the actors that you're seeing in this network are independent RL agents, which are sharing rewards up the hierarchy and so on. And you can essentially use whatever you have trained for a store when a new store comes online. Right. So the store, in some sense, knows how to manage a store, right? And so you can create a copy of this for a new store, and it can adjust later, but at least it will have something to start with as an initial policy, right? So that's what we have done, and we have got one publication out already last year, and another is going to be submitted soon. And interestingly, this work is also part of one of our TCS products called Optimera, and it has gone into the real life as well, into real life applications. So that is something I think we are more proud of than anything else. And in the last 5 minutes, I just want to talk about the things that have come out of these real world applications, but which are more abstract or more researchy, I would say. Right. So the on the left hand side is a problem that was inspired by the fact that when we have variable sized problems, which we talked about earlier, the optimal reward you get can also vary from instance to instance, right? So if you have a railway system and a different number of trains running every day, the optimal delay that you get when you're recovering from a previously delayed state can be different for every instance. And so you cannot really use the reward as is. And so we came up with this idea of when training, can we actually improve on our own performance, on the algorithm's own performance, and use that as a feedback to improve the both the rate at which the algorithm runs as well as reduce the variance across while we are learning. And so we found that we could actually do this in a nice analytical framework, and we could even show that it converges in expectation. And this was the subject of a short paper in AMAS last year or this year. And on the right hand side is something we have published very recently in CIKM, where and this was inspired by our supply chain work, where we know that you don't get products instantly, right? So if you want something from a warehouse or if the warehouse wants something from a vendor, you have to wait for a certain amount of time before those products can be delivered. And so to actually get that working, we found that we could create a delay resolved DQN, a small modification to DQN, by augmenting all of the actions that have not been implemented so far, even though we have thrown out the decision, but it has not been applied to the system. So if you just append those to your states, then we get what are called augmented states, or so-called information states. And this concept already existed before, but in a table-based form. And we were able to show that using deep reinforcement learning, the complexity or the size of the state space doesn't blow up very much, and you still get very good performance on top of what a standard DQN could do. Right? And finally, there was the requirement to have better sample efficiency. And there were some works already in this direction where you use the same representation, the same latent representation to give out different objectives. So I believe there have been papers on throwing out or rather predicting the policy or the action and the value and the next state reward. But what one of my colleagues, Hardik, and I figured out was that instead of predicting the next state reward, if you could actually predict the next state's latent representation, okay, and this latent representation would be coming in from an LSTM because you don't have full observability. So you have partial observability. That's why you use a bunch of previous time steps. And if you, instead of predicting the original observation, which could be very high dimensional, if you just predict the next state's latent representation, it actually gives you much better training of the representation itself, the latent representation itself. And so this is what we use to show that you can get much more reliable results out of the same size networks. So finally, if we come back to the key question that I showed earlier, right, that it's a struggle to find the right definition of the problem itself. Then I want to leave you with a few questions that you might want to pursue as a student as well, right? So, I mean, obviously, there are questions about offline RL and causal RL in all of this, which I'm not going to go into because I'm sure you have thought of them already. But the remaining questions are maybe something that you have not thought of so far, but that you might find interesting. So, for example, are there any characteristics of the transition function f, right, that make convergence harder or easier, right? And when I say transition function, I'm also talking implicitly about the simulation, right? So how much fidelity should the simulation have to ensure that you converge to a good policy is something that we have not looked at so far. Then can we actually link these models? So you have a simplification in a simulation. How bad can it get in the real world? So can you actually predict that using the properties of F? Or out of all the ways you can say define the states and actions for a problem, is there a one way of defining it which is the best, right? Based on some metric which I have not even thought of yet. uh, or how much does your partial observability cost you, right? So this should not be state to action, but rather a state to observation emission function. So how much is the loss in that function causing you in terms of the potential for final reward? And finally, uh, we know that when we do reward shaping, there is a high possibility that the algorithm is going to do some kind of specification gaming, right? So is there a way to protect against this systematically? So are there some versions of reward or some ways of defining the reward that are less likely to result in specification gaming than others, right? So maybe these are all questions that some of which at least you might find interesting to think about. So with that, I'll stop and maybe we can take questions. I'm not sure, Professor Ravindran or Martina, how we want to handle it.
So there are questions in the Q&A panel. I mean, I could read out those. Meanwhile, there are a couple of hands up. Can we take those first?
Sure.
So, Dr. Vijendran, do you want to ask your question first?
Yeah, thanks, Ravi. See, I was interested to know about the Konkan Railway problem,
Mhm.
and I was curious to know, is the line capacity considered as a constraint, or the station capacity considered as a constraint? So that is question number one. And two, what was the, though it was not deployed, what was the result in terms of delays, reducing the delays in the entire capacity?
Right. So the first answer is that we were considering both kinds of capacities. So we had actual data from Konkan Railway for what are the minimum halt times required for, say, a given train at any station, and the minimum running time on a piece of line or the line section. And so we had to implement those anyway. So if it takes 30 minutes to run on between two stations, it takes 30 minutes. So that is part of the simulation. Only after the 30 minutes are completed is the train eligible to take the next move. So it can move into the station or it can wait at the entry signal to the station. So both capacities were considered, and the result was that at least in simulation we could show that there was a potential for 20% or so improvement or a reduction in secondary delays. So yeah, that was there, but I mean the bottleneck came in because they were not able to connect up the IT system, the actual data gathering from the real-time system to the controller very effectively. And in the meanwhile, I mean, Konkan Railway was absorbed by Indian Railways as a whole. So the whole, management structure changed and then it got dropped.
Okay, thank you.
Sure.
There is a follow-up, not really a follow-up. There's another Konkan Railway question in the chat in the Q&A board.
Right. I'm
So, what
trying
was
to.
the reason for the Konkan Railway solution not being used in practice, though it was a success in proof of concept?
Right. So I think that is really it. The IT problem of connecting the system up to the real-time data, and the management change when KRCL got absorbed by Indian Railways.
Sure. So, Sashank, you had your hand up. You want to ask the question? I'm going to allow you to talk. You can go ahead and ask the question. You can unmute yourself, Sashank. Okay, so he is not responding. So I'll let him whenever he wants to.
Okay.
So, Martina, you have your hand up.
No.
Okay. So here is another question. Parameterize, this is from Rohit Singh. Parameterizing the travel between cities only on population and distance could have been more helpful if we give weights to metropolitan cities. Was this considered?
Well, yes, right. So metro cities will have more population. So when you multiply the populations of, say, Bombay and Delhi, it is going to have a much higher weight than any two smaller cities, or even Bombay and a smaller city. So in that sense, you do get a lot of emphasis on the metro cities, and in fact, you can see this in this map as well. I don't know if you can still see my screen, but
Yes.
yeah. So the connectivity graph here, you can see that there are strong links between the 4 or 5 metro cities around India, right? And much lower, weaker links between everything else.
Yeah. So we have one more lockdown question. In the lockdown problem, can the district-wise agents work together, or are their decisions independent of each other?
Right. So ideally, we would have liked to make them interact and coordinate, but in the paper so far, or at least what we have worked on so far, they are completely independent. So there's no higher level agent which is doing any coordination, and they are not talking to each other either.
Okay. So is there anything you can do to predict how this latest variant will behave using RL?
Uh, Yes, but we would still need to get the
I
disease
know.
model from healthcare people, not from the RL people, right? So that is really the bottleneck, because there's a very high variance in the parameters of the disease in general.
Yeah. Yeah. So last one more question from Prabhu Chandran, right? What are the state of the art oral algorithms that you have considered in the solving industrial problems.
Right. So
Open-ended.
yeah, it is a bit open-ended, and I'm also restricted to mentioning only things that we have published. But I think the most complex one that we have done in a real-world situation is DDPG. For some of the supply chain work, we have not even gone to TRPO or PPO for real-world problems yet. For the reasons I mentioned earlier, right? That once you have simplified the problem enough to be able to model it in a modest amount of compute, we find that there isn't much difference between the various algorithmic options. And so we use the simplest one that works.
Is this one more audience member put their hand up? Errol, do you want to ask the question? Go on. We can't hear you though. Okay, Rohit?
Hello.
Yeah.
Yeah, go on.
So my question was like regarding the metropolitan cities. So the outflow from the metropolitan cities was like fairly large compared to the travel between other cities. That's why I was saying like weighting the cities, like because the people travel from like cities like Delhi, Bangalore to outside to other cities was much larger as compared to between the smaller cities.
Correct. And so
And population doesn't like truly reflect the weights.
okay, there are two parts to the answer. One is that obviously this is not a very complex or realistic way of modeling a network. Right? We were just trying to see if we could, the simplest possible way of defining the network flow could be actually get realistic results, and we were able to project the results fairly closely. The second part is that if you look at the amount of people you expect to arrive, and if you think of that as a multiplication of two populations, then clearly we say between Bangalore and another smaller city, you would have the same number of people. But proportionally speaking, those number of people would be a much larger fraction of the population of the smaller city than it is for Bangalore. Right. So when you take fractions of how many people are going to arrive from a certain place, even though the same number of people are traveling to from one way and in the opposite direction, the proportions become very different. Right. So it is a fairly standard way of doing network modeling, in fact, for population flows.
Okay.
So I think we are past the time. So let's thank you, Harshad, for a fantastic talk and also taking all these questions.
Thank you. Thanks for inviting me.
And we hope to see you here more often.
Yes, I
Thank
would
you.
be happy to. Thank you.
Yeah, take care.